All of us know that even the briefest glance of the sun through your telescope or binocular will probably permanently blind you, right? Mm-hmm. Okay. And if you don't know if your equipment's any good, don't use it. Okay. Lawyers, are we good? Okay. Just had to check that. So, as I said, I started back in 1979 observing and sketching the sun. And in the past few years, I became a little bit more proficient in recording my observations, both in drawings and in imaging, both white light and in hydrogen alpha. Though I find I can image the sun like that, number one, the sun is really blank this year, so there's not a whole lot to see or image. But I like drawings. It seems like I see more in the drawing than with the image sometimes. When I put together this program, it dawned on me it's been 40 years since I've started this, so that's a long time. And in that time, I've seen the rise and fall of sunspot cycles. Let's see, there's the laser. This is solar cycle 21, solar cycle 22 that peaked in about 1990, and I had just a couple, 3 years off of observing there. Solar cycle 23 and solar cycle 24, which is winding down right now. So these solar cycles, they rise and fall about every 11 years. The solar cycle that we are on is solar cycle 24, and you can see that this is a monthly chart of my sunspot numbers starting in 2008 till January of this year. The solar cycle peaked in about 2014, but every month it varies quite a bit. And what's fascinating now is that some astronomers speculate that we may be headed for a very protracted solar minimum where we might not see many sunspots for the years to come. Naturally, this comes when I get my equipment just about perfected. So a little bit of history here. What are sunspots? These are sunspots. They're on the photosphere or the surface of the sun. They're dark regions. And sunspots are generally cooler than the rest of the sun. The sun's photosphere is about 5,700 degrees Kelvin. These are a couple thousand degrees Kelvin cooler. That's still awfully hot, but they're cooler than this part of the sun. That's why they look dark. And they are areas of magnetic disturbances on the sun. All sunspots have a darker region called an umbra, and most sunspots have a lighter area around them called the penumbra. And sunspots are magnetic disturbances on the sun. So if we imagine this as a cross-section of the sun, way down below here we have the core of the sun giving out tremendous amounts of heat and radiation, the radiative zone where radiation is coming out, and near the last couple 100,000 miles of the sun's radius is the convection zone, where hot plasma rises and cool plasma sinks. Well, in that convective zone, we have magnetic fields developing. And where the magnetic field pops out of the sun, it doesn't allow as much of the sun's heat up, and that causes a sunspot from our point of view. How this is believed to develop is the sun, different than our Earth, rotates at different speeds. Our Earth, being a solid ball, all rotates in about 24 hours. The sun, however, being a ball of plasma, rotates at different speeds. The north and south poles rotate in about 30 days. The equator rotates in about 25 days. So if we have lines of magnetic force going from the North Pole to the South Pole, they will soon be stretched out and going faster at the equator, and over time, these magnetic lines will be stretched out. If there's a kink in the magnetic line, we get a sunspot out of the deal. And notice that our sunspot usually has a North Pole and a South Pole, just like our magnets. So our sunspots have south and north poles, and notice that each hemisphere has a different polarity. Here in this drawing, we have north, then south. In this hemisphere, we have south, then north. And sunspots come and go in cycles. Again, it's about an 11-year sunspot cycle. This is a fascinating graph. We are about here on the graph, up in 2019, but you can see there's been times of high sunspot numbers back in the 1940s and 50s in particular. It was called the modern maximum. Back in the 1820s, we had what was called the Dalton minimum. And most fascinating, in the 16 and 1700s, we had the Maunder minimum. Basically, from Galileo's time till about 1715, sunspots were not recorded, which is a fascinating thought. Why weren't they recorded? The thought was maybe the astronomers weren't good enough, but no, they made great discoveries at that time, like Cassini's division and things like that. So it turns out there probably were not sunspots. What other strange event happened on Earth at this time? Guesses are free. It got cold. What was it called? Little Ice Age. It did start earlier. Is it an exact cause? Don't know. But it's interesting to think, hey, what if this happens again now? But that'll be for later. Yeah.
So sunspots, they occur in pairs?
Yes.
And do they wax and wane at the same time?
Yes. Yes. Well, bring up that point about they come in pairs. Usually they do, but right now activity is so weak, we're lucky to see anything. Okay? So this is cycle 24, our current solar cycle. It peaked in 2014, and this is an optimistic drawing, by the way. The solar cycle being 11 years actually is twice that, 24 years for the magnetic solar cycle, so the magnetic field gets back to where it was originally, 22 years. Again, our last solar maximum was in 2014. Well, I like this graph. It was updated in April of this year. And you can see two possible points we're going at. We're right here. We're either going to really lose sunspots in the next few months, or they will come back fairly strongly by the end of this year. So stay tuned. A bit of math is involved in looking at sunspot numbers. The sunspot numbers by the Wolf method are calculated as R equals 10G plus S. So what does that mean? R is the sunspot number. You'll see that quite a bit throughout the show here. G is the number of groups. And S is the number of individual spots. So if we have 3 groups and 20 spots, the sunspot number is, well, there's our formula. R equals 10G plus S. We have 10 times the 3 groups plus the 20 spots. So our sunspot number is 30 plus 20, which gives us 50. Now, Jeremy did not tell you before you came, but you have a test. This is a close-up of one of my drawings. What's the sunspot number? How many groups are there?
2.
Does everyone agree that's 2 groups?
Yes.
They're widely separated. How many individual black spots, umbra, do you see there?
3.
Right there? Okay, 3. 1, 2, 3. How many over here? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11? 11 and 3 is 14. So our sunspot number is what?
34.
34. 2 times 10 plus 14. Got it?
Is that supposed to account for spots on the other side of the sun?
It is. This formula was made back in the 1800s. And you and I would both say there's 14 spots here, right? But I guess it was to account for what's on the back side and such, or what your telescope is too small to see. Seems like a goofy formula, but we're stuck with it.
I think the reason they did that was that they weighted, they thought the groups were more important. A group is a more important entity than a spot. And that's why they weighted it that way.
And a problem I have when we have a lot of sunspots, you know, these groups can be close together. So when do you have two groups or one big group? And I get into arguments with people about that every now and then. Here's another test. This was right before the eclipse. How many groups are on the sun today? One group, right? How many umbra do you see here? 1, 2, 3, 4, 5, 6, 7. How many?
The red and the blue?
The red don't count now.
Okay.
1, 2, 3, 4, 6, 7, 8, 9. Is it 9?
12.
Yeah, 12. So our sunspot number is what?
22.
22, yeah. Have I lost you yet? You didn't know you'd have math tonight, did you? And sunspots are classified. This goes to a question you had earlier. The easiest way that sunspots are classified is through a method of A through H, where A-class sunspots are just one little dot up there. B-class sunspots are a group of little spots. A C-class sunspot, one of the sunspots has a penumbra, the other one doesn't. A D-class sunspot, there's at least two penumbras, the gray areas around the sunspots. The really nice sunspots are the E and the F-class sunspots, which are huge. This is 20 degrees across on the sun. That's huge. They're very rare. And H-class sunspots is just one big spot with a penumbra. So that's the sunspot classification. The E and the F-class sunspots, like this one is an F-class sunspot, they're rare. And at this time of the solar cycle, they're non-existent. But this was 2 years ago.
Now, you say they're drawings?
Yeah, that's a photograph.
Are you?
That's a drawing.
You're going to talk about how you
Yeah.
prepare drawings?
Yep.
That's right, that was on your outline.
So we also have these AR, these active regions. It turns out sunspots are numbered by NOAA, the National Oceanic and Atmospheric Administration. So we have sunspot group numbers. So what do? How do I do this? Most of the time I use just a simple telescope. 2017 I made 300 observations of the sun. Now I know the guys in the back of the room were saying, it's been so cloudy this year, and it has, hasn't it? But 300 observations is pretty good. Last year, almost as good, 295 observations. And most of the time I just used a 60 millimeter refractor. Simple telescope, okay? And it had a Lunt Herschel wedge. I had 55 power. Very simple setup. The only thing complicated about it was this Herschel wedge. It is like a diagonal on a telescope, but what it does is it reflects almost all of the sun's light out of the view, so you can safely view the sun, and it gives a very, very sharp view. And that, to me, makes all the difference. It makes a really crisp view. But again, we're talking a 60 millimeter telescope, nothing fancy. And with that setup, I make daily drawings of the sun, kind of like this one here. And from these drawings, I calculate the sunspot number. So after I draw it, I say, okay, there's one spot there, there's two spots there. There's way too many spots there to count right now, but that's where I get my sunspot number. If you're interested in doing this, a whole lot easier, more common way to do it, to make white light observations of the sun, is to put a filter on the front of your telescope that reflects out almost all of the sun's light. Here we have one on a Celestron telescope. They could be made of mylar, they could be made of glass. It reflects the sun's light out before it enters the telescope, and they're relatively inexpensive and they work just fine. When you're observing the sun in white light, which is just all the light of the sun, where you see the sun like this, you will not only see sunspots, hopefully, but you'll see faculae. And faculae are brighter regions around sunspots. Can you see that brighter area there? And they're best seen near the solar limb. It turns out this is a little darker than this part of the sun, so you can see these. So this is a fascinating little point here. The faculae are hot regions around sunspots. What temperature are sunspots in general?
Couple thousand degrees.
Well, cooler, right? When the sun has a lot of sunspots, cool regions, it also has a lot of faculae, warmer regions. So it turns out during sunspot maximum, we actually have a warmer sun with more sunspots. Right now, with the sunspots almost non-existent, the sun is actually a tad bit cooler than it was a few years ago. Now, if that were to persist for many years, then we'd probably get some cool down out of the deal. Faculae, again, are hotter regions of the sun's surface. When possible, when seeing conditions or when time allows, I try to make hydrogen alpha observations most of the time these days with a Lunt 50 telescope. That means its objective here is 50 millimeters across. And it's a nice little telescope. You really can see some incredible detail on the sun. If you're interested in hydrogen alpha observations, there are 3 big companies in America that do the hydrogen alpha observing. The Coronado Company, they make the PST telescope, you may be familiar with. Lunt has beautiful solar telescopes. And Daystar specializes in solar filters, and right now their main one is the Quark that they're selling right now. All of these are very nice. They're all expensive. I said $700 and up. But on the used market, you might get some of this, like a PST, for what, $350? $400? If you really want to go all out, you double stack your filters for hydrogen alpha work, and then you'll see a lot more detail on the chromosphere, and I'll show you what that means coming up. So what that means is on the PST, there's another filter here. On the Lunt Solar Telescope, there's another filter here. And the Quark just comes like this. It already is double stacked. But the problem is double stacked kind of means double price. Something to consider. But again, 300 observations a year, whereas we struggle to get those nighttime observations. So this is what happens with me when I have my telescope out. I have a pre-made form for observing the sun that I made, and I sketch the position of white light features like the sunspots and the faculae on this form. And I actually find I can do it with a lot of precision because basically I can be looking in the eyepiece here with my right eye, because I'm right-eyed, and with my left eye I hold my clipboard that has this form on it just at the right distance, and I can match up the sunspots with what I'm seeing in the right eye with the form, and you can get right on target with it. Kind of neat. If time and all allows, I do use hydrogen alpha, the Lunt 50 telescope as well, and I add in things like the prominences here and occasional filaments and flares that I'll talk about later. Then, once inside, I make a clean copy of that same drawing and I add the prominences in and the flares and all that stuff that may be there. Then I scan that drawing, and in Photoshop, I crop it, I add a little bit of noise to make the sun a little textured, add color, and I add text to it. And then with that, I can email this to the British Astronomical Association and the American Lunar and Planetary Observers. So without much equipment, you can send in real reports to these organizations. I know we have some great imagers in this room. I've met some of you. I'm not that great on imaging. I do a little bit of imaging, both either in white light here or in...
Wait, just please say that.
I didn't do it.
I think it's the projector.
The light's on.
Yeah, you went off.
All right, I want to thank you guys for coming out.
Great to meet you. And,
This room is just, we got this screen, we got this projector.
It comes at the right price.
Q&A.
about those donations you were asking about.
Yeah, so we're not going to solicit any donations.
Projector would really be nice, though, and they're $500. Your computer did something, too.
Oh, good. Oh, yeah, that's this.
About 3 weeks ago, we were announcing Calgary.
So if the projector just is overheated, it has to cool for a few minutes.
Hey, do you need to be plugged in?
I'm plugged in.
Oh, okay, you are.
It's a projector issue. So that's our intermission. There we go.
Okay, thank you. Whew, that was close. So, sometimes I image in white light or in hydrogen alpha, again, if there's interesting things. And the camera I use is a ZWO ASI 120 camera. It's pretty cheap, it's easy to use. If I can use it, it's got to be easy. It's a lot like taking a picture of the moon. You just kind of get it on the computer screen, you focus it and take the picture. The only problem is if you image the sun in hydrogen alpha light, when you're looking at prominences and flares, you get things called Newton's rings. It doesn't show real good because it's not real dark in here, but they're annoying lines on your image and caused by interference. And the way you cure this is you tilt your camera ever so slightly. The majority of my program is going to be next about what's been on the sun the last few years. A brief synopsis, not much, but enough to be interesting. In 2017, the first half of the year, the sun was about blank. I mean, that's a typical look at the sun. There's not much there, but there are a few features in hydrogen alpha. So I bring up the point that in hydrogen alpha, the sun was usually pretty interesting. And as the year went on, in April and in May, there were occasional sunspot groups here and there that made it interesting. And I'll show you several times tonight that you go out and you never really know from day to day what it's going to do. And right before the eclipse in July, activity really began to pick up on the sun. We had some nice sunspot groups that I could even image here. And as the eclipse approached on the 21st of August, the sun had a remarkable upsurge in activity. Now, I've shown you this drawing before to practice on sunspot numbers. Here's a photograph in hydrogen alpha light. That bright area right there is a plage. The best I can describe that is above the sun's surface. We have the photosphere of the sun. The next layer up is called the chromosphere. This is a bright, hot region in the chromosphere. It is not a solar flare or prominence. It's just basically a bright area on the sun. And it's associated with solar activity like this sunspot group that's coming around. So on the 17th of August 2017, that's a nice looking sunspot group right there. There's a nice prominence shooting out of the sun right there. The 18th, we get a little more activity here, a little more activity here. On August 20th, the day before the eclipse, this is an F-class sunspot group, as big as they come, right on the solar meridian. If the sun had produced a large flare at that particular time, it would have been, from this sunspot group, it would have been aimed right at the Earth. It did not, though. And on eclipse day, which you remember, there were sunspot groups, right? And this sunspot group was just gigantic. An F-class sunspot group, but there was other activity behind it as well. Then the next month, in September of 2017, the sun was more active than it was for a long time. The zenith of the solar activity was in September 2017. There was, let me go back. This huge, huge sunspot group that we saw the month before during the eclipse. And pay attention, there's this one measly little sunspot down here that doesn't look like anything. On September 3rd, we have that big sunspot group, and this one below it starts to look, well, different than it was the day before. And on the 4th, things are getting pretty active here. By the way, this takes forever to draw something like this. When there's no sunspots like today, it's a breeze. This is probably 45 minutes outside. September 5th, look at this big sunspot group, and this is just growing like crazy, right? And on September 6th, my goodness, look what happened there. September 7th, it's still growing. It's nearing the western limb of the sun here on September 8th. And on September 10th, 2017, I saw a huge solar flare right here. I just happened to be out at the right time and to catch it. Solar flares are classified as A-class solar flares, B-class solar flares. Those are the ones we get any day right now. M-class solar flares we very rarely get right now. They're pretty big. And the X-class solar flares are the huge ones. On September 6th, we had an X 9.3 flare. That is huge. It was the largest flare in a decade. The one I observed right here was an X 8.2 flare, which is really big. I was lucky to see it at that time. This, by the way, is a prominence shooting off the sun probably 100,000 miles. Well, the sun takes about 27 days to rotate. So 27 days later, in late September, those sunspot groups were back, but quite a bit faded from what they were before. By the way, when they rotate around the next time, they change their numbers, okay? NOAA changes their numbers, but this is what we saw during the eclipse. And then, in the middle of October, they came back again. I showed this nice prominence on the sun's limb where it was coming around. And here we see in late October, these sunspot groups are still around, but by the end of October, they are just about gone. By November, they're gone. But in their place, was a huge, huge filament. See, that looks like a frown right there? That's my drawing. That's an image of it. That's what was in the place of that big sunspot that produced the flare in September. Filaments are prominences, projections shooting out of the sun, but we see them from the top. We're seeing them edge on, okay? The rest of 2017, solar activity plummeted, not too much happening, but again, I love seeing all those prominences on the limb of the sun there. 2018, another slow time. Not too many sunspots, but there were some nice views again of prominences in hydrogen alpha light, and sometimes I could get pictures of them. Here we see in April of last year, pretty blank sun, but we have a filament here, we have prominences here. We see a puny little sunspot last April. Here in May of last year, just little sunspots, trying to show you there's not much happening there. But even with not much happening like this little sunspot, there's a pretty nice prominence to look at.
Those prominences, do they look stationary through your telescope?
They look stationary, yes, but if you look at it right now and go back out in 15 minutes, or take an image now and in 15 minutes, you'll note change. I mean, they change, but it's, well, but think of it, you're talking something 100,000 miles across, it's moving. I show these drawings in May to show you that, hey, the sunspots are kind of coming and going. Here's some little ones. Here it is on May 10th. You'll see this one just fading away here. This one, the one that was here, is now what they call a pore. And I get in trouble with my reporting groups on sunspots. When a sunspot is no longer a sunspot, it's called a pore, which is just the remains of it, just a tiny little thing, too small to be called a sunspot. I got in trouble the other day because there was this great big pore that I thought was a sunspot. So where's the line between a little sunspot and a big pore? But such is the life for solar astronomers. Here we see this sunspot fading away and fading away 13th of May. Now on May 14th, the sun is blank. May 15th, the sun was blank. But we still see some filaments here and there. May 17th, we see some prominences, but no sunspots. May 18th, filaments, prominences, no sunspots again. May 20th, the same deal is going on. But by May 21st of last year, hey, there's another sunspot up there. And I leave a little question mark with its number because I was probably one of the first ones to see it, probably even before NOAA, so I gave it a number, which is the next number to be given. Last May, we had a strange occurrence with 3 sunspot groups on the sun, which is rare these days. We had a nice D-class sunspot right there last May. And a year ago today, there were no sunspots, but there were some really nice prominences. The next little sequence I show you of 4 days is going to show you the birth of 3 sunspot groups. Here on the 17th of June of 2018, there's nothing. The next day, the 18th, there's 2 sunspot groups. And on the next day, the 19th, we have 3 sunspot groups. So you never know what you're going to see from day to day. The following day, the 20th, again we have 3 sunspot groups. And the following day, we're down to just 2 sunspot groups. So you never know, again, you'll see on the sun. Sunspots seem to be in bands north and south of the equator. Late in the solar cycle, they're fairly near the equator of the sun, near the center of the sun. So they line up here. You'll see that from time to time in these drawings. Lining up in the north and southern hemisphere. But as you can imagine, as 2018 continued to go on, sunspot activity continued to drop. But as I keep saying, in hydrogen alpha, you can still see prominences and filaments every now and then. These filaments, again, are prominences that we see on their edge, so they look like little lines on the sun. Here's some prominences. And we see little filaments. So as last year ended, the sunspots again were few in number, but again hydrogen alpha views were interesting. And this trend continues to this time. In fact, we have had a very quiet 2019. The entire month of February, no sunspots were seen. And that's only happened about 10 months in all of history that we know of, that a whole month went by with no sunspots. But luckily, a little bit of uptick in activity since then. Some are speculating that sunspot numbers may soon be rising, but again, some are speculating that the sunspot numbers may wear out. So a little summary of this. Here we are in cycle 24. We started with a real low sunspot number. Between this in 2007, 8, 9, and 10, we had very few sunspots. The sunspot numbers peaked in 2014, and now they're dropping off fast. So the sunspot number has been decreasing, and this is anticipated as the solar cycle is heading towards a minimum. I've been comparing my observations to some others. I like this graph. This is the AAVSO, the American Association of Variable Star Observers. They count sunspots. The British Astronomical Association, they count sunspots. And me and all of our observations match up pretty good the last 2 years. Which I liked that graph once I got it to work. But some of the things I've tracked is like the number of spotless days, the days with no sunspots. They have generally increased per month the last few years. Now this was back in 2008. We had almost 100% some months with no sunspots. This is 2015 forward to the present day. We have quite a bit of spotless days, but not as bad as 11 years ago. So the thought is there may be more blank suns still to come. In looking at my sunspot observations, I saw in 2017 the sunspot number was 20. Last year the sunspot number was 6.3. Back in 2017, about a quarter of the days were spotless. In 2018, about 63% of the days were spotless. This year, it's about 57%. And on this graph, I show a rapid decrease in the number of sunspots and spotless days. So the next solar minimum may be protracted. In red, I'm showing you the number of spotless days. And I just arbitrarily set in blue the number of days with 100 sunspots or more. And you can see that number is going down rapidly, right?
Does the period between heavy sunspot activity, is that generally constant in years
It's generally an 11-year cycle, but...
of activity, and then when there's a nadir, no?
Well, no, from one peak to the next is 11 years. But I was just reading last week, in fact, that if the solar cycle is longer, generally the activity is weaker. And converse, if it's a short solar cycle, stronger activity. And you can really see the activity has been going steadily down. The next solar cycle, which is scheduled to start any time now, may be very weak. Some solar researchers say even non-existent, which is a bummer if you have solar equipment, by the way. So we may be entering a period of very low solar activity. Remember I talked about the Maunder minimum at the beginning of the show? Are we entering that? Well, think of it. We normally can't forecast the weather very good, can we? I'm thinking we don't know exactly what's around the bend. So, only time and...
We're entering that phase, and there's a potential correlation between the Earth cooling. Then the global warming guys are a little off base.
Well, it may be a blessing if the sun, let's just say that what I said is right. If there's few sunspots, it cools the Earth, right?
Right.
Well, let's just say that happens. And let's just say greenhouse gases are warming the Earth. Maybe the net effect will be kind of neutralized.
Right.
We're probably luckier that way than if we were gangbusters on sunspots right now. Then we'd probably be, the sun would be contributing more to the heating of the Earth. So it's an interesting question. Yes, sir.
Has there been a cause found for the 11-year cycle?
Yes, that was, what happens is, remember I told you that inside the sun, we have the core of the sun where the nuclear reactions are taking place. It sends out radiation about halfway up the solar radius. And the last 2,000 miles of the sun's radius is the convection zone where heat rises and sinks. The plasma rises and sinks. Well, between the line between the convection zone with this rising and sinking of the plasma and the radiative zone, there's a sharp break there. The radiative zone basically turns as one unit, solid like the Earth. But the convection zone turns slower at the poles and faster at the equator. That causes a magnetic field real strong right there. And it turns out that astronomers believe there's basically like a conveyor belt that takes 11 years to cycle between the equator and the pole, and that controls the sunspot cycle. And for the last 10 years, they've been saying that conveyor belt is going really slow or not at all. So that's why they're saying this next future might be very low on solar activity. But again, we don't know. Only more observations will tell, won't they? So what I've done today is I've shown you with very simple equipment and just a little crazy time, you can make a lot of observations of the sun each year. This is 300 observations a year. One year I had 329 observations. That's a lot. But get out there, look at the sun, and simple equipment, you can do it. So, until next time when we meet again, when we may be discussing the new Maunder minimum. That's all. It's Sunspot Baby by Bob Seger.
That's what that is.
Before we leave though, there are some great books on observing the sun. Probably the best book by Erica Ricks, Solar Sketching. I mean, it shows you great tutorials on what to do here. Much more involved than I ever could do. There's some books on solar observing techniques and safety you can find on Amazon. This one, I don't think it's in print anymore, but the Solar Astronomy Handbook. It has everything and much more than that you'd ever want to know about the sun. And a great history book is The Sun Kings. This talks about the guy, Richard Carrington, who saw the first solar flare back in 1859 and the effects it had on the Earth, which was really amazing. Any questions? Freddie.
Go ahead. Oh, just a comment. One other resource for a solar observing handbook is the AUVSO site. They have in 2017 they published.
Oh, they got a new one now?
Yeah, it was updated as of I forget, October 2017. Anyway, aavso.org, and go to the Sunspot, the solar section, and it's there. You download it.
Okay, thank you. Thank you. Yes, sir.
Yesterday, I was talking on a group of ham radio operators, and there was this person that showed an article that was published on space. And there is a group of scientists. I took it with a grain of salt, and I hope you do too. There is a group of scientists in Germany that is relating the 10.7 GL cycle to a conjunction of Jupiter, Earth, and Venus.
One of the questions was what causes the 11-year sunspot cycle, and every once in a while you find something weird, like it's the relationship of Jupiter pulling on the sun, and no. Maybe that's why it's the Astrological Society.
Yeah. we try to weed them out.
When the moon is in the 7th house.
Other questions? Yes, sir.
On that small scope, you said you just use a Herschel wedge.
Yes.
What protects the innards of your scope
No,
from projecting that?
nothing.
Overheat, or you know more about it?
Because all the light is going through the just through the objective to the Herschel wedge.
You cannot use a very big telescope. Right?
Yeah. I think 4 inches is about as big as you could go with that. But that gives really sharp views.
I have a question.
Yes.
So the sun has been described as a variable star.
Yes.
And I'm assuming it's because of the sunspot activity. Can you elaborate on that?
The
Variable star. The sun is a variable star.
in the regards of when there's more sunspots, it actually produces more radiation, more heat because of those faculae. We get a few more watts here on the Earth when there's a lot of sunspots. And when there's fewer sunspots, we're actually a little bit cooler.
So it's in terms of power output, essentially.
Right. But to you and I, in normal life, we wouldn't notice it. But, if it's protracted, it could be interesting. And the question back there, what will it be in 10 years? We don't know.
Okay, any other questions? All right, applause.
Well, thank you very much. Thanks, Jeremy.